All right. So let's have a look at this here. So for question number 1, give them a mark for their givens. The mass was 200 kilograms. The initial speed was 2 meters per second. Final speed 8 meters per second. Okay, the distance over which that happened was 13 meters. Okay, their second mark, work is a change in energy. This is a work energy theorem question, so they'll get a mark for doing that. Okay. Then what we have to realize is since it is a change in energy and we have two different kinetic energies, we have to actually do this final minus initial thing. Okay, so that's what we're doing here. Force times distance is 1/2 mv squared, mvf squared, sorry, minus 1/2 mvi squared. All right, to manipulate to find the force, all I do is divide both sides by d. Okay, they get a mark if they did that. All right, so if they divide both sides by d, they've got the change in energy over d equals F. All right, give them another mark for plugging in their numbers. 1/2 of 200 times 8 squared minus 1/2 of 200 times 2 squared divided by 13. And they should get that required, for their fifth mark, 461.5 newtons of force. Okay, they must have the units, and they must be the right units on that answer. If they do not have units, it is not right. Okay, and that's not half off. They don't get that mark, period. Okay. Questions on that one? Okay. Okay, for our second one, now we've got a change in potential energy question. Okay, first one was change in kinetic, this one's change in potential. Give them a mark for their givens. The work done is 450 joules, the initial height is 13 meters, and the mass is 65 kilograms. Okay, give them a mark for work as a change in energy. Okay, maybe they went directly to mghf minus mghi, it doesn't really matter. Okay, if I want to get if I want to get HF by itself, the first thing I need to do is add MGHI to both sides. Okay, so this term here needs to move over to this side by adding it, and then I would divide both sides by MG. So if they arrived at this, okay, you can give them another mark for having it properly manipulated. Okay, next mark is for plugging in their numbers. 450 joules plus 65 times 9.81 times 13 divided by 65 times 9.81 gives us the final height. Okay, the final height for their fifth and final mark is 13.7 meters. So not much higher than it started. Okay, again, make sure it's got units on it. Okay. Give them a mark out of 10, hand it back to them, double check your name is on it, and then hand it in, please. Alright, so reminder, June 2nd. Okay, June 2nd is going to be the unit exam, okay, for this unit. Be ready. That's giving you just 1 day under 2 weeks notice. Okay. Alright, what we got to talk about today is a continuation of what we were doing before, which was work energy theorem. Now we got to talk about conservation of energy. All right, what we mean by that is when there isn't any work being done, what happens to the energy that is already present in a system? Okay, it could be used to do work, but in this situation it's not. Okay, the energy is in there. What can happen to it? Well, in the perfect physical world, it has to stay there. Right? Energy can't be created, it can't be destroyed. It can be transferred away, that's work. We're saying that can't happen right now. Okay? We're saying there's no work being done. So, it can't be created, it can't be destroyed, that means it needs to remain unchanged. All right? Now, the most common example we have of this for this unit is a roller coaster. So let's say I've got this roller coaster. It starts up here. Okay? Up here, it's very high off the ground. What kind of energy would it have there? It would have potential energy. Okay? Would it, if it was also moving at that point, have some kinetic energy? All right. Let's say that in total, okay, when I add those two types of energy together, its total mechanical energy is 1,000 joules. How much mechanical energy does it have down there? Remembering that energy can't be created, it can't be destroyed, and we're not losing or transferring any energy anywhere along the way. 1,000 joules. Okay? The law of conservation of energy says very simply this. The initial energy of a system equals the final energy of the system if there is no work being done. All right? Because work is a transfer of energy. If work's being done, that's not true anymore, is it? Okay, because I would lose some energy or I would gain some energy depending on whether I'm doing the work or whether the work's being done to me. Okay, so in this case, there's no work being done. The energy at one point is equal to the energy at the other. All right, so the same amount of mechanical energy, 1,000 joules at both points. But do I have the same amount of potential energy down here as I had up here? No, I don't. Okay, I can't because I'm much lower. I can't have more potential energy. All right, what do I have more of at the bottom? I have more kinetic energy. Why? Because usually at the bottom of a hill you're going faster compared to the top. All right, so I have the same amount of mechanical energy, or in other words, I have the same total amount of energy. What's happening is I'm changing it from potential to kinetic as I ride the roller coaster. At the higher points, more of it is potential. At the lower points, more of it is kinetic. Does that sort of make sense? Okay, I mean, if you were riding your bike or your skateboard down a hill, okay, then certainly you know how that works, right? At the top, right, you've done all that work to climb to the top, or maybe you cheated and someone drove you to the top, I don't know. Okay, you get to the top, you've got lots of potential energy, and as you roll down the hill, you go faster and faster and faster. Your height decreases, and you gain kinetic because you're going faster, right? Your amount of energy, top and bottom, are the same in the perfect physical world. Okay, in the real world, is your energy at the bottom the same as it is at the top? It isn't. Okay, be thankful for that, because if it was, you'd be going really, really, really fast at the bottom of the hill. Okay, be thankful that there's some drag and friction and stuff like that that takes energy away. Otherwise, you'd probably get the speed wobbles about 3/4 of the way down, and you know what happens once you get those. Okay, they're pretty much unrecoverable, right? And then usually you're going over the handlebars of the bike, which means that your energy is used to do work on the road. That's generally not good for you. Okay, so what should you wear if you were to engage in a behavior like this? A helmet and pads, okay? It never ceases to amaze me how many people ride bikes and skateboards down gigantic hills without any protection whatsoever. Okay? I call that natural selection. Okay? If you are unwilling to protect your brain, it will cease to be useful to you later. All right? So protect your brain. All right. So when energy is transferred to an object, what do we call that? What's a transfer of energy? Oh God, we just spent 2 weeks on it. Blank is a transfer of energy. Well, okay, good. I was getting a little worried there. Okay, so when energy is transferred to an object, it can cause a change in both kinetic and potential energy. So in other words, when work is done, okay, it can change both the kinetic and the potential energy. If you were pushing, let's say, a wagon or a stroller up a hill really fast, okay, are you changing both its kinetic and its potential energy? Yeah, you're making it go faster and uphill. So you're doing work. You're changing the mechanical energy of both. All right. A ball thrown upward has kinetic energy because of its movement, but it also has potential energy because it's above the surface of the Earth. Okay. So potential and kinetic energy are very closely related, so we often just add them together to get the total mechanical energy, okay, which is defined as the energy due to the motion and position of an object. In other words, mechanical energy is kinetic energy plus potential energy. Okay, everybody all right with that? Does that make sense to everybody? Let's try an example here. I have a 3 kilogram baseball, 0.3 kilogram baseball. 3 kilogram baseball would be hard to throw, kind of heavy. Okay, is thrown in a straight line through the air. Okay, meaning its height is not going to change. Everybody with me on that? That's physically impossible, by the way, but we're going to say that theoretically that could happen. All right, at a height of 2.50 meters above the surface of the Earth, it has a speed of 20 meters per second. What is the total mechanical energy of the baseball? All right, it's 2.5 meters above the ground. Does it have potential energy? Okay. It's moving at 20 meters per second. Does it have kinetic? All right. Do I have a formula that can calculate both of those kinds of energy? Yes, I do. All right. I can calculate kinetic energy using 1/2 mv squared, and I can calculate potential energy using m times g times h. All right, so it's just a matter of me doing both of those calculations and adding the two numbers together. All right, so to calculate the kinetic energy, I'd go 1/2 times the mass of the baseball times the speed of the baseball squared, and add that to the mass of the baseball times the acceleration due to gravity times the height above the Earth. So when we do that, we find that it has 60 joules of kinetic energy and 7.36 joules of potential energy, meaning it has a grand total of 67.4 joules of mechanical energy. All right? Is that a very difficult calculation? Just plugging in numbers, right? Like you don't even really have to do any manipulating for this. All right. Now, the illustration here in figure B212. All right, this is work energy theorem stuff, okay, the drawing back the bow. All right, so if I'm an archer and I draw back this bow, what am I doing? Work, okay? To draw back the bow, I have to exert a force over a distance. Agreed? What am I putting in the bow? Well, no, work is a transfer of energy. So if I pull back the bow, I do work. That means what's now in the bow? Energy, okay? What kind? Potential energy, the elastic potential energy due to the fact that the bow wants to snap back to its original shape. Right? When I let it go, it will try and pull the string back to its original position. When it does that, if there's an arrow sitting in it, what is it doing to the arrow? It launches it, which is essentially is it exerting a force on the arrow over the same distance I pulled it back? Okay, so all that work I did, force times distance. When I let it go, same force, same distance, all that potential energy was used to do work on the arrow. The arrow will now have what? Kinetic energy, right? It'll be moving very, very fast. All right, that's the science behind that. Okay, now, here's what we have to understand about that. If I do, let's say, 300 joules worth of work in drawing back the bow, how much energy can the arrow have? I did 300 joules of work. The maximum amount of energy in that system is 300 joules. That's all it can have. It can't have more. It can't have less. Okay? It's law of conservation of energy. When I let the bow go, all 300 joules of potential energy are transferred to the arrow. Now the arrow has 300 joules of kinetic energy. All right? Is that essentially what we were doing before when we were doing these problems? Right? Is that what we were doing? We calculated the work, and that was the energy that was now in the system. Okay? It's essentially the same thing. All right. I want you guys to try 8, 9, and 10. All right? They're relatively straightforward. Okay? Easy calculations here. Okay? I want you to give them a quick try here. All right? They're just like what we did here with the baseball. Okay, so let's have a look at number 8 here, first off. Okay, so on number 8, we've got the Seagull carrying the Clam. All right, so it's flying horizontally at 8 meters per second. So does it have kinetic energy? Yes, it does. Okay, and it is 30 meters above the ground, so it also has potential energy. All right, so if I want to calculate mechanical, we just got told that mechanical is equal to the kinetic energy plus the potential energy. And we have a formula for each of those. Kinetic energy is 1/2 mv squared, and potential energy is m times g times h. Okay, I know m, I know g, I know h, I know m, and I know v. So I can calculate this no problem. I just have to plug in my numbers. All right, so 1/2 times 0.3 kilograms. Why do I have to make it 0.3? Why can't I use 300 grams? It needs to be in kilograms to calculate energy, guys. A joule is a kilogram meter square per second squared. You must have the mass in kilograms. All right, and it was moving at, what, 8 meters per second, so times 8 squared, plus 0.3 times 9.81 times 30 meters. All right, so we'll plug that into our calculator here. All right, so 0.5 times 0.3 times 8 squared, okay, plus 0.3 times 9.81 times 30. All right, so we got 97.89 joules as our answer there. Okay, everybody with me on that one? All right. How are we doing on number 9? Are we stuck on number 9? Yes? We need to go over number 9? Yeah. Right. Okay, so for number 9, we've got the 55 kilogram high jump athlete. Right. So we know their mass, and we know that they leap into the air in an attempt to clear the bar. At the top of the leap, they have a total mechanical energy of 3,000 joules. Okay, that's 3 times 10 to the 3. And they're moving at 8.33 meters per second. So as they go over the bar, they're obviously above the ground. Do they have potential energy? Yes. And they're moving at 8.33 meters per second, so they also have kinetic energy. And they tell me what those two energies add up to. The only thing I don't know is the gravitational potential energy. So let's have a look at our formula again. Mechanical energy equals EK, which I have enough information in this question to calculate, plus EP. And I don't have the height, so I can't calculate it using m times g times h. Agreed? How can I get EP by itself? Right, subtract EK, right? I always do the opposite. If I want to move something, I'm adding these, so I would subtract. Right, so the mechanical energy minus the kinetic energy should give me the potential energy. Right, so now I just plug in my numbers, or plug in my formulas here first. This I was told was 3,000 joules minus 1/2 mv squared. So 1/2 times the mass, 55, times 8.33 squared should give me the potential energy. Agreed? All right. So when I plug in my numbers there, 3,000 minus 0.5 times 55 times 8.33 squared. All right, leaves me with 1,091.8 joules of potential energy. All right, I'm going to give you guys a few minutes to try number 10 here, because it's very much like what we were doing here, except this time we're looking for EK. So I'll give you a minute to try that one. Okay, so number 10 works very much like number 9, except instead of looking for EP, we're looking for EK, right? It says calculate the kinetic energy of the hammer. Well, since they tell me the mass, and they tell me the height, and they tell me the mechanical energy, I have enough information to get, well, I have this number. I have enough information to calculate that number. This is the one I'm looking for. So how do I get EK by itself? Subtract EP over to the other side. All right, so I'm going to have EM minus EP equals EK. So when I plug in my numbers there, I've got my mechanical energy, 1,880 joules, minus 2 kilograms times 9.81 times the height, 50 meters. Okay, and that will give me EK. So when I plug that in, I've got 1,880 minus, okay, in brackets, 2 times 9.81, probably didn't have to put it in brackets, times 50. All right, so it already has 899 joules of kinetic energy, and it's still 50 meters above the ground. Is this a hammer you want to be under? No. All right, it is not, because when it gets to the ground, it's going to have 1,880 joules of kinetic energy, and that could do a lot of work on you. Okay, i.e. changing the shape of whatever part of you it happens to hit. Okay, that's why if you've ever been downtown when they're working on one of the high-rises, they always have that covered. They always cover the sidewalk. Okay, they have that kind of scaffolding, and they cover the sidewalk up, so you're walking in kind of a tunnel. That tunnel is there to protect you from construction debris that might fall off the top of buildings, because it could do a lot of work on you were it to hit you. Okay, all right, 899 joules. Okay, so is this making sense? All we're doing is manipulating this formula right here. Now we're going to get more complex than that as we go along today, okay? But that's where we're starting at. Okay, so let's look at this problem here. This kind of puts the work energy theorem stuff together with the law of conservation of energy stuff. If I use an average force of 100 newtons to pull back a bowstring half a meter, okay, the bow is aimed vertically. So it's just like the picture that we saw here. Okay, this girl has got the bow aimed vertically upwards. All right. So if she does this, she pulls back with 100 newtons, half a meter. How much work has she done on the bow? Well, how do I calculate that it's 50 joules? Force times distance. Okay, the force is 100 times 0.5 is 50 joules. Everyone with me on that? All right, if I do 50 joules worth of work on the bow, that should mean then that there is 50 joules of potential energy in the bow. Because the law of conservation of mechanical energy says you can't create energy, you can't destroy it. So once I've done that work, that energy is in the system and it can't go anywhere else. Okay? How much kinetic energy does the arrow have? Well, we talked about this earlier. Okay? We said if I let the bow go, then the bow will do work on the arrow. Okay? Since the bow only has 50 joules of energy in it, it can only give the arrow 50 joules of energy. Okay? So the final kinetic energy of the arrow is 50 joules. All right? Now, what's the gravitational potential energy of the arrow at its highest point? So if I fire the arrow from ground level, okay, it's going to fly upwards. And as it flies upwards, it's going to slow down, slow down, slow down, and eventually reach its maximum height where it stops before falling back down. Okay? At that point, it has 50 joules of gravitational potential energy. Why? Because that's all the work I did on the bow. It's all the work the bow could do on the arrow. It's all the kinetic energy the arrow had, and it all got turned into potential. You guys follow me there? Okay. Once you put work into a system, that energy is always going to be there. So let's say I know that the arrow has a mass of 0.250, that's probably not that heavy, 0.050 kilograms, 50 grams. Could I calculate how high this arrow will go? Okay. How much energy can the arrow have when it's at its maximum height? 50 joules. So I know then, okay, that this is 50 joules. I know the mass is 0.050 kilograms and g is always 9.81. Can I calculate the maximum height of the arrow? Yeah, all I got to do is divide by mg. Okay, and I've got the maximum height of the arrow, which in this case, okay, so the arrow would go 101 meters into the air. All right. All right. So I want you guys. Oh, there's what I was looking for. I knew I had the answers on there somewhere. Okay. Anyway, law of conservation of energy. So this is kind of the next step from here. The total amount of energy in any given situation remains constant. That's why we can say that EI, the initial mechanical energy, equals the final mechanical energy. Okay? Because once it's in there, it can't be created or destroyed. All right? So, thus the amount of mechanical energy remains constant. In the absence of outside forces, kinetic energy can be converted into potential energy and vice versa, which is what we said happened with the arrow. Okay? We bent the bow, put elastic potential energy into the bow did work on the arrow, gave it kinetic energy, that kinetic energy became potential, and when it falls back down, that potential energy would turn back into kinetic. Okay? Everybody with me there? All right. So what we want to do here is look at this example. I have a 1.5 kilogram rock, and it is dropped over the edge of a 30-meter cliff. Okay? What's the speed of the rock just before it strikes the surface of the lake? All right, so if I reach out over the cliff, what kind of energy does the rock have? Potential, because it's 30 meters above the water. Everybody follow me on that? Okay, can I calculate how much potential energy it has? Okay, I know the rock's mass. I know it's 30 meters above the ground, and I always know g. All right, so that would be its initial mechanical energy, because if I'm holding it, does it have any kinetic? No. All right, so it only has potential at the top. Okay. However, when it hits the ground, or the water in this case, what kind of energy does it have? Kinetic. All kinetic. Because what's its height when it hits the water? 0. All right. So what we're saying is the initial energy equals the final energy, and in this particular case, that means the potential energy at the beginning equals the kinetic energy at the end. That's not always the case, but it is the case in this example. Okay? Everyone follow? Right? What is the case in every Newton or in every law of conservation of energy question is this: the initial potential plus the initial kinetic equals the final potential plus the final kinetic. Okay? Now, we simplified this because we said if I'm dropping it, it's not moving, and it doesn't have any kinetic energy at the beginning, and since it's hitting the lake at the end, it doesn't have any potential at the end. So we went to this. EP, mgh, equals ek, 1/2 mv squared. Right? Everyone follow how we did that? Right. So I want to figure out how fast it's going. How do I get v by itself? Zach? I don't want to divide by v, I want to leave v there. Take this stuff out, okay? Move the other stuff. Leave v where it is, okay? Move half of m over to this side. Now, I got m on the top and m on the bottom. What happens to m? Can I cancel it? Actually, in this case, I can. I'm multiplying everything, so I could cancel it. I don't have to. We won't here, but we could cancel it. Okay? And I'm looking for v, not v squared, so I've got to square root this. Right? Now I can solve for v. Okay, so v is going to equal then the square root of 1.5 times 9.81 times the height, which is 30 meters, okay, over 1/2 times 1.5. All right, so that thing's going 24.26 meters per second when it strikes the lake, which is exactly what they have, 24.3. Okay, everybody follow me there? It's just algebra. Okay, it's nothing too terribly difficult, but you are going to have to flex your algebra muscles a little bit. Okay, warm them up, stretch them out, because you're going to need them. All right. Okay, what I want you guys to do is try these two, 11 and 12. Okay. All right, so for number 11, okay, again, this balloon is dropped from a height of 12 meters, okay? We know that since we're comparing 2 points, we're doing a law of conservation of energy question, EI equals EF, right? Now, we can go ahead and write out all of this stuff, EPI plus EKI, okay, equals EPF plus EKF. We can write all that out, but we don't really need to if we're smart enough to figure out what kinds of energy it has at both points. Okay? If I'm dropping it, just like the example we did, it doesn't have any kinetic energy because it's not moving. Okay? Similarly, when it hits the ground, it doesn't have any potential energy, so I'm left with this. Potential initial equals kinetic final. So m times g times h equals 1/2 mv squared, and I'm solving for v. So I divide both sides by half of m. Okay, and square rooting that, okay, to get rid of the square. Everybody with me on that one? Yes? Okay, so when I plug in the numbers in, okay, v is going to equal 10 times 9.81 times 12 meters, okay, the initial height, so that's m times g times h, divided by 1/2 times the mass, which is 10. Okay. All right, so we got 15.3 meters per second. Okay, now, earlier I said when we look at this, we see that we have mass on the top and mass on the bottom. Those masses can cancel. All right? If that's the case, let's just double check and make sure. All right, so I'm just taking the masses out of that calculation I just did. Okay? Look at that. I get the same number. Okay? Same answer, 15.3. Why? Because the mass of the object doesn't change while it's falling. It's the same object. Right? So there are going to be some cases where you can cancel the mass. In fact, I have in the past given a question where I talk about law of conservation of energy, and I don't give the mass. Okay? This concerns people. All right? Because if they don't remember that mass isn't necessary for a question like this, they come up to my desk during the exam and they say, Mr. Coder, I think you made a mistake on question 5. You didn't give us the mass. And I say, oh, my mistake. The mass of the roller coaster is 200 kilograms. And that person happily walks back to their desk and does the question. Another person walks up to me and says, Mr. Coder, I think you forgot a mass on number 5. Oh, silly me. The mass of the roller coaster is 10,000 kilograms. You should see people's eyes when I give a different mass the second time. It's like saucers, man. Okay? They get huge because, oh, I must have done something wrong. He gave different numbers to both of those people. I'm screwed. And people just start to panic, and I laugh. Because you don't need the mass in a situation like this. It's the same roller coaster or the same rock or whatever all the way down. Its mass isn't changing, so its mass is irrelevant because all things fall at the same rate. Okay? Don't let that happen to you. Usually I don't do that anymore. Usually I just put the mass on there to avoid the problem. Okay? It was funny that day though. All right. How many people have got number 13 done? All right. Try number 13. It's very similar to what we just did, except this time you're not looking for V. This time, you're looking for H. Okay, so give 13 a try. All right, so for number 12, same idea. Okay, EI equals EF. Rather than write out all of those, let's just decide what we have at the beginning, what we have at the end. So the child jumps on a trampoline, okay, vertically into the air with an initial speed of 1.6 meters per second. All right, calculate how high the child will rise. So we're assuming that this trampoline is one of those ones that's actually on the ground and they've dug out underneath it so that it can bounce. What's the initial height of the trampoline? 0. Okay? Does it have, what kind of energy does it have then at the beginning? No potential because it's on the trampoline and the trampoline is on the ground. Okay? So there's no potential, but they have an initial speed of 1.6 meters per second. So they have kinetic energy at the beginning. Okay? Calculate how high the child will rise. So, when you're at your highest point, how fast are you going? 0. Okay? Because at your highest point, you've slowed down, slowed down, slowed down, and you're just about to change directions and begin to fall back down to Earth. Okay? So your speed at that point is 0, means you've only got potential energy at your maximum height. So we're back to this. 1/2 mv squared equals m times g times h, and they want to know how high the child will go. So I'm looking for h. That means divide both sides by mg. Okay, what'll happen to m? It cancels. Okay, you don't have to cancel if you don't want to, but it does cancel. Okay, and I'm left with this. 1/2 of v squared over g equals h. So 1/2 times 1.6 squared over 9.81 will give me how high the child goes. And they only go 0.13 meters. Well, that's like this far. I mean, if you're little, that's probably very exciting. Okay, for you or I, well, what do you do? Jump harder, I guess. Okay, making sense? All right, so a couple of other examples here. Okay, as we move around, okay, as we move away from the Earth's surface, if we're not under power, okay, we begin to lose our kinetic energy because it gets turned into potential. If we're falling towards the Earth, it's the other way around. We lose our potential because it gets converted into kinetic. Now, this pulley here, right? If I've got this pulley, I've got two masses hanging on it. Agreed? If I let it go, what's going to happen? because one mass is bigger than the other. So what's going to happen? Right, the larger one will go down and the smaller one will go up. Is work getting done? Okay, is energy being transferred? Okay. When I'm looking at this though, okay, this one's going to move down and this one's going to move up. So right now they're both stationary. Is there any kinetic energy in this system? Okay, there's only potential. When I let it go and this begins to move down, it's going to gain kinetic energy, agreed? But it's going to lose what? Potential. This one is going to do what? It's going to gain potential and kinetic, because right now it's stationary. How can that be? If I only have, let's say at the beginning of this, 500 joules of energy, I can't make energy, can I? There's only 500 joules of energy in that system. Okay, so this one, the 2 kilogram mass, is actually doing some work on the 1 kilogram mass. All right, but the total energy of the whole pulley system in both masses still remains at 500 joules. All right, what that essentially means is they're not going to fall at 9.81 meters per second squared like something you just drop would. All right, the reason they won't, the 1 kilogram mass is going to slow the 2 kilogram mass down, because the 2 kilogram mass is transferring energy to it. This one's taking energy from this one, okay, but the total energy of the whole system stays at 500 joules. All right. Otherwise, pulley systems would make energy and break the first law of thermodynamics, okay, and they can't do that. Everybody with me there? Yeah? All right, so we already did this one here with the bow and arrow, so we'll skip that one. Okay, and I want you guys to try these here. Okay. Okay, give those ones a try. They're just like what we've been doing. Okay, so we got the 20 kilogram or 20 gram dart. How many grams in a kilogram? Oh, okay, good, 1,000. Okay, kilo means 1,000, guys. All right, so you're going to have to divide this number by 1,000 to get this into kilograms. Okay, is moving with a horizontal speed of 4.10 meters per second. It gives us the total mechanical energy. Wants us to calculate the gravitational potential energy of the dart. We've done a couple like that already. Okay, that's easier than the EI equals EF thing. Okay, pendulum. Pendulum is a 500 gram metal ball suspended on a 50 centimeter string. Okay, it's pulled up 10 centimeters at the bottom of the arc. Mechanical energy is 0.491. This one's like a good one. It's tough, okay? But I think you guys can figure it out. So I want you to try these two here, and hopefully we'll get a chance to go over them both before the end of class.